everybody. We're gonna start the session very soon. Just reminder for all of you that you can ask questions either in the YouTube channel or in the Matrix chat whenever you want during the session. We will then ask them to the speaker at the end of the talk. So thank you all for attending. Our next speaker is Luca Denti. He is currently a postdoc researcher at Comenius University in Bratislava. He obtained his PhD in this university in Milano Bicocca, and he had worked on many different aspects of bioinformatics. And more recently, his main focus is on both pangenome and structural variation. And in this talk, he will talk about pangenome graph augmentation from unassembled long reads. Thank you very much, Luca, for accepting this invitation, and please, you can start.
Okay. Thank you for inviting me. So yeah, today I will move a bit away from structural variations. And yeah, this is a work in progress. So everything that you will see, it's under development. So it will change, I hope. And the results will be preliminary results that I have. But I hope that you will enjoy it. So I will start with what is a pangenome. So maybe you already know it, but this is what is a pangenome for me. So a pangenome is just a collection of genomes, and you can see it as a set of strings, so a set of genomes, or like a graph encoding the multiple genomes. And in this graph, in my view of a genome is like an haplotype. In this presentation, a genome will be like an haplotype. So a genome will have two haplotypes, but I will just use haplotype or genome. In the same way, that is an assembly that is also a path. So when I talk about path in the graph, I will talk about genomes or haplotypes, because in my opinion, most path in the graph theory definition of path are just unlikely a combination of two haplotypes. Okay, so this is my definition of pangenome. It could be a set of strings or a graph encoding those strings. And well, this is just an introduction. So why pangenomes are useful? And I think that everything can be summarized with this sentence that is from the HPRC, the Human Pangenome Reference Consortium website, that says that no single genome can represent the diversity in the human population, and pangenomes can fix the reference bias and the observational bias that is created by considering a single reference genome. But yeah, this is just to say why we're interested in pangenomes, but actually the focus of my talk will be in how can we build the pangenome. And actually, this is the list of tools that I found for building a pangenome. Like we have Pandora, that is for bacteria mostly, Pampa, that is for proteomes, and then we have PangeBlocks, PGB, and some other based on minigraph. And we can split the approaches right now in three categories. So we have the approaches based on multiple sequence alignments of the assemblies, like the first three. And then we have other approaches that are mostly based on the all versus all alignments of the input assemblies. And then we have the progressive methods. But the main drawbacks of all these approaches is that they require high quality assemblies because they start from full genomes mostly to build the pangenome. And actually, as we have seen with the T2T project, producing a high quality assembly is quite costly because you need multiple sequencing technology to get high quality representation of a genome, and it's also computationally expensive. And just a note, I know that minigraph can work also with reads, okay? But for the construction of a pangenome, it has been designed for assemblies from what I understood. So all the approaches in the literature are based on building a pangenome from assemblies. And I will focus on the last category, so progressive construction of a pangenome. And this is a picture from the minigraph GitHub repository. And these kind of approaches can be described as follows. So a graph can be progressively constructed by iteratively aligning and inserting one genome at a time. So we will cycle between these two steps that are the alignment and the augmentation. So you start with a single genome, then you align a second genome to it, and then you augment the original genome with new information from the second assembly. And you keep doing this. And in the end, you will have the graph with all your assemblies. So I will, based on this idea, my proposal is that maybe we can construct a pangenome in a progressive way, but starting from long reads. So my goal with this idea, with this project, is that I want to provide an assembly-free and also alignment-free approach for the progressive construction of pangenome. Alignment-free because I tried several long-read alignments to graph, and they wasn't that reliable. So, but maybe I should try the gggraph that we saw this morning. Maybe it will improve things a bit. So my problem is I have a pangenome, GFA file, a set of reads, FASQ, and I want to augment the pangenome with read information. So with all the information that is not already in the graph, but that is in the read sample. And well, to tackle this problem, there are several questions that I will need to find an answer for. So for instance, since I want to be alignment free and assembly free, so I have the reads. So the first question is, how can we pinpoint differences with the known genomes? So you have your genomes, how can I know which reads cover new portion of the genome? And then once I know which reads or which portion of the reads contains new information, how can we locate such differences in the graph? Because I don't want to align the reads. And then finally, since we have a coverage, so we don't have just one read, how can we summarize information coming from different reads? So this is the problem. And this is mostly the approach that I'm proposing. And I will guide you through the various steps. But the general idea is that I have my pangenome, I index it somehow, then I compute these strings that are specific strings, and then I can anchor them to the graph. And then based on this anchoring, I can cluster them. And then I can create cluster of specific strings. And each cluster will provide us information on what is the new information that is in the read set and not in the graph. And I can use this cluster, I can locally analyze this cluster and then augment back the pangenome with this new information. But yeah, now I will guide you through all the steps just to give you more details. So I will start with the first part, so that is mostly the indexing of the pangenome. So I rely on both representation of the pangenome. So I will have a string-based representation and a graph-based representation of the pangenome. So starting with the string-based representation, I take the path in the graph, so the haplotypes, and I index them using an FMD index. So just a bit of introduction, what is a FMD index? But I will start with an FM index that maybe it's more common. So it's a self-index for strings. So you have the data and the index in the compressed structure, and you have small size and full text searching. So you can compute the number of times a pattern occurs in linear time with respect to the length of the query. So the count operation and also the locate operation. And this index is based on the BWT permutation, and maybe you saw it as a pair of counts array and rank structure, but yeah, it's just a brief introduction. Maybe you already know it. And what is an FMD index is the FM index of a bidirectional collection of DNA sequences. So I just take all my sequences like R1, R2, Rn, and I concatenate them with the reverse and complement. And then I can build a single index for both forward and reverse strands. And this index allows in constant time, backward extension, and forward extension. So it would keep the same time complexity of FM index. But in constant time, you can also forward extend your query. Indeed, by backward extending, this is just the main message of one of these papers. So these are 3 papers on this topic, all from Ang Lee. So the first one was the Fermi assembler, because the FM index was first introduced there, and then it was improved by Ang Lee. And lately, this last year, we provide a very fast implementation of the FMD index that I will use, and I will show you how. But the main message is that by backward extending a pattern with a base like an A, we are also forward extending the same pattern with the reverse and complement of that. So this is just the main idea that you can. The main idea. It's one of the ideas in that paper. But yeah, anyway, this was just an introduction of the data structure. And this for the string-based representation. So I have my path and I index them using stringology-based index. For what concerns the graph-based representation of the graph, I use inspired by Kimmer sketching mostly. I sketch the graph using solid anchors. So you can just think at the sketch as a map that map a Kimmer to some vertex of the graph. And what is a solid anchor for me is any chimer that occurs in only one vertex of the graph and that occur less than number of time path in the FMED index. So this just to take all the vertices, all the chimers that are not that repeated in the graph or in the haplotypes and that are not informative enough to uniquely place or anchor my strings somehow. So I want mostly unique chimers, and this is the definition that I use for my solid anchors. So I have just a map, chimer vertex. Okay, so this is the first step, so the data structure that I will, on which all the approach is based mostly. And the second step is how can we determine how to pinpoint the differences between the reads and the graph. So I have the graph, I sketched it, I have the index, and I have the reads that may contain new information, new portion that I should include in the graph. And to pinpoint differences, I use these specific strings that we introduced a few years ago. So this is the definition of specific strings. So given two sets of strings, any set, any strings, a specific string is any substring that occurs in T and that doesn't occur in R, in the set R, as a substring. So here an example. So if these are our two sets, AC, R and T, we can see that the only difference is this T. So we have a T in R and A in T. So the set of specific strings is this quite huge set. So we have a quadratic number of specific strings, but are all the substrings of T that do not occur in R. But this set is quite huge, so there is a second constraint on the definition. So a specific string is any substring occurring in T and not in R, such that no other specific string is contained in it. So we can reduce this set as just these two strings. And on top of this, we can also merge all specific strings overlapping on some T, on some input string, so that we reduce even more the number of specific strings. So I will use these to pinpoint the differences with respect to the haplotypes in the graph. And why with specific strings? I mean, in this paper, we proved that specific string pinpoint any difference between the two sets of strings, and in the context of bioinformatics, if we index a reference genome, then specific strings pinpoint mostly all the variations with respect to the reference genome. But in this work, I'm trying to understand what happens if we index a reference pangenome. Can we say that our specific string pinpoint mostly all unknown variations, so all the novel variations that are not already in the graph? So this is one of my goals. And for those of you that are more in the chimer world, why not using specific chimers? So this is a question that most of the times pop out. Well, specific strings cover more variation. We proved that specific strings cover more variation because they have variable length nature, so they are not fixed to K, and they are also easier to compute than not specific chimers. Okay, so specific string. We have the specific string that pinpoint all the differences. So we know from each read which portion of the read is not in our index. So we are not in the haplotypes. So now we need to anchor these specific strings to the graph somehow. We don't have alignment information. So this is a work in progress. It's one of the steps that can be improved by a good margin. But yeah, a specific string is a substring of a read. So in Python notation, we can say that a specific string is just start at P and of length L, so goes to P plus L minus 1 included, but anyway. And this substring is not in the haplotypes because it's not in the index. It's specific to our read sample. To anchor this string to the graph, what we do, we just search for solid anchors in the neighborhood. So we use some sort of seeding, okay? So we look at the part upstream to the specific strings, and we select a set of solid anchors on the left. Then we select a set of anchors on the right. So we have two sets of anchors on the left and on the right. And then we try to pick the best pair. So with best, the definition of best is the pairs of specific strings that are the closest on both the read and the graph, and that are collinear on at least one haplotype. So they occur in the same haplotype at least one, because we don't want to allow recombination in this phase of the idea. And then once we have found this best pair, we just extend the specific string to include the two solid anchors. In such a way, we know that the anchors are unique in the graph, in the vertices, in the vertex set of the graph. So we can say, okay, I have this specific string, it starts and it ends with these anchors. So I can say this specific string should go in this subgraph that goes from this vertex to this other vertex. And in such a way, in this way, we can anchor the specific string, so we know the specific strings from which part of the graph come from. Okay, and then the last part of the approach is that we try to cluster somehow the specific strings, and then we analyze the clusters. So now we have anchored specific strings that we can see them as a tuple, like RPL, so the read, the position on the read, the length, and the two solid anchors. And we can cluster them based on where they have been anchored. And we use a sweep line algorithm to do so. So we first sort all specific strings by the left anchor based on their position on the graph. Oh yes, one thing that I forgot to add to the slide, we assume for this step, specifically for this step, we assume a DAG, so then no cycles and a quite linear topology. And then we create a cluster with the first specific string, that is the leftmost one. And then we iterate over the remaining string while keeping one open cluster. So if the new specific string overlap with current cluster, we add it to the cluster. Otherwise, we close the current cluster and we create a new one, and we iterate over the strings and in this way we create clusters based on their position on the graph. Now we have the clusters, and each cluster represents a specific portion of the haplotypes of the new individual, because they are portion of the reads that have been anchored to the same region of the graph. So most likely they should come from the same portion of the haplotype of that individual, of that new individual. And we are sure that those portions are not in the graph already. What we need now, we just need to summarize the information contained in each cluster to understand how to augment the graph. And actually there are some challenges, like specific string may come from different haplotypes because we use unique anchors, so solid anchors. And due to ploidy, we may have specific string coming from different haplotypes in the same cluster, so we need to discern from which haplotype they come from. And there is also another problem, always due to ploidy, but also due to sequencing errors, is that in the same cluster, and by how the clustering is done, specific string may overlap and they may not share anchors. Okay, so this complicates quite a bit everything. So I will, for the sake of this presentation, I will just won't consider this set of strings. So we can assume that in a cluster, all the specific strings start and end with the same anchor. Okay, there is some steps that hidden in the approach, but I won't explain them. So a cluster, we can consider a cluster as a triple, A, B, S, where A, B are the left most anchors and B is the rightmost anchors on the graph, and the set of specific strings that we placed on that subgraph that goes from A to B. So we need to analyze this cluster. So what we do, first we split the cluster based on the specific string length. This will take into account heterozygous variation of different length on the two haplotypes. So every time this ratio is greater than this R, that is a parameter, we say, okay, the specific strings should come from the same haplotype because their length is quite similar. Otherwise, we split the cluster. And then we have the cluster that could have been split in two. And what we do, we create one or two consensus per subcluster using partial order alignment. And we rely on ABPOA. And in such, when we have a single cluster, so we haven't been able to split the cluster by length, we still may have two different haplotypes, like a multi-allelic SNPs, multi-allelic SNPs, so different allele on both haplotypes. So the length of the specific string should be the same, but we can create two consensus while doing the partial order alignments in those cases. And then when we have the consensus, we can locally align back the consensus to the graph. So we know the subgraph because we know that this cluster starts from a vertex A, so from the leftmost anchor A that is on a vertex, and ends at B, so another vertex. So we can extract the subgraph. So we locally align the consensus, but actually we don't align the consensus back to the graph yet, but we just consider all the unique haplotypes that goes through the two nodes and will locally align the consensus to each path, and then we select the best alignment. And then we use this alignment to augment the graph. And to do so, we rely on VG augment. Okay, so this was mainly it. So this was the approach. And although it's a work in progress, still have some experiments and some results. So I tried some real graph that I built from DCF. And I simulated read samples. And my goal with this experimental evaluation was to check the reliability of our sketching scheme. So my definition of solid anchors is reliable enough. So can we actually use them on real graphs? And then to evaluate the accuracy of our graph augmentation. So just to see if we can trust our results. So we start with the first one. So the experimental settings is this one. So I have the VCF on the T2T reference from the HPRC. I build the graphs with increasing number of individuals, and then I sketch the graphs. So I build my sketch. And then I check the distance between two consecutive solid anchors with respect to the T2T genome. These two, the main goal was that if two anchors are too far away from each other, then we may miss that region, because if the two anchors are far away, like let's assume that we have I5 reads, so we should expect an average read length of 15,000 base pairs. If two anchors are more than that distance away, then we won't be able to anchor any read in that region. Okay. But what we found out, so the results are only on 3 chromosomes, so chromosome 1, 11, and 20, and the distance is 15,000. Just considering this 3 chromosome, 99.996% of the anchors are very close, so they are 100 base pairs apart. So even when we consider 32 samples from the VCF, so it seems that we may anchor reads on most all the regions of the genome. And from the plot, we can see that blue is the length of the chromosomes, and the orange part is the number of base pairs that we miss with our anchors. And I checked those here on the chromosome 32, so these red parts. And actually, we have 285 missed regions that we miss, but they overlap non-repeats or segmental duplications. So they are quite complex regions of the genome, and this is the distribution of their length. So some of them are quite big, so 8 million base pairs. So we are missing quite big chunks of the chromosome, but I mean, the overall message, I think that it's most of the region, almost all the genome can be covered by solid anchors. We will miss something, but this is still a work in progress, so we will focus on those regions later. But still, big parts of the genome is covered by solid anchors. And so we can trust our solid anchors. We can use them to anchor our specific strings, at least on most part of the graphs. And then the second experiment was to evaluate the accuracy of our augmentation. So the setting is this one. We build the graph with increasing number of individuals, also from the VCF or from HPRC. And then we simulate a deployed read sample from an individual X that is not in the graph, so some sort of leave-on-out experiment. And then we augment the graph with the corrected reads. Corrected, we use I5 ASM because we simulated I5 reads. So we corrected them just to remove all sequencing error, mostly all the sequencing errors, not all, but just to have clean reads. And then we align the reads back to the graph with minigraph. But which graph? So we have several graphs in these settings. So we have the original graph, so the full graph with the n individuals plus the x individual that we removed. So this is the full graph. Then we have the one-out graph, that is the original graph with just the n individuals without the x individual. And then we have the augmented. We augmented the n plus x graph, that is the full augmented. And in this, if we augment the full graph, we shouldn't expect to augment anything because the individual is already in the graph. And then the augmented n graph, that is, we take the graph with the n individuals without the x individual and we augment it. So this is the most common scenario where your individual is not in the graph and you want to augment it from long reads. And how we evaluate the accuracy of our argumentation using these two metrics, so some sort of recall and some sort of precision. So the recall is the alignment's accuracy against these four graphs, and the precision is the percentage of novel vertices and edges that we added to the graph and that are actually used by the alignment. Okay, and also here it results only for one chromosome, but it looks still quite promising. So in this plot, so on the left plot, I plotted the edit distance of the distribution of the edit distance of the read alignments against the various graphs with increasing number of samples. So what is nice to see is that if we increase the number of samples in the graph, the alignment to the one out, that is I align a new individual to a graph without that individual, the accuracy, we can see that it improves because the edit distance becomes lower. But this is expected because the more individuals I have in the pangenome, the less differences I should expect with a new individual from the population. But what is nice is that even in the hardest case, let's say, so I have just one individual in the pangenome, we can see that the blue one is the read alignment against the full graph. So I have that individual in the pangenome, and this is the distribution of the edit distance. If we align the read sample to our augmented graph, so the one out augmented, we can see that the edit distance is mostly similar to the one using the full graph. So meaning that our augmentation should do what it is expected to do mostly. And this improves even for more samples. And on this side, instead, I plotted the distribution of I did a pairwise comparison between the sum of the graphs, so like full versus one out, of the number of matches. So I took from the alignments how many matches each read has in the alignment, and I just did the difference between the two numbers on the two graphs. So full minus one out. So for each read on full, how many matches minus how many matches the same read has against the one out graph. And we can see that if I compare the full versus the one out, the number of matches is different. Okay, so we have the median at 1, and this is just because SNPs dominates our analysis. So these are mostly all the SNPs. We have a lot of SNPs that are in the individual and not in the graph. So if we compare the alignment to the full graph and to the graph without that individual, all the SNPs will produce at least one in the read, one error. So one less match in the alignment. But what is nice that the same behavior, we can see the same behavior even if we compare the one out augmented with the one out. And if we compare the full versus the one out augmented, we can see that the number of matches is almost always the same. And yeah, as before, we can see that the difference between the graphs decreases if we increase the number of samples. But still, it means that our augmentation seems to bring the one out graph our augmentation allows to produce a graph that is way more similar to the full graph, and that can be safely used to align the reads, in my opinion. Okay, there are some issues. So this is so these were the results on the recall part, and these were the results on the precision part. Okay, so I will present them like this way. So it was how many, we augmented the graph with vertices and new edges, and we wanted to check if these vertices and edges are actually used by the alignments. All the vertices that are not used by the alignments, it means that we added them they are wrong because these are simulated data, so we shouldn't expect to add new vertices that are not aligned to. And well, there are some errors here. So here I plot in blue the one out augmented and the full graph augmented. So we can see that even in the full graph, even if we try to augment the full graph, so the graph with all the individuals plus the X individual, if we augment that graph with the individual that is already in the graph, we are still adding some vertices and some edges to the graph. So we still have some issues with the precision. But the same occurs even for the augmented, for the one out. So for the one out, we have way more novel vertices, but some of them are not actually used by the alignments, meaning that we, we may have some issues with the precision, with our definition of precision, but still it's quite high. I mean, 95, 90, mostly 90 or 94% of the vertices that we added to the graph are actually used by the alignments. And the same for the vertices, for the edges. And here I plotted the support that we have on all the novel vertices. And we can see that in the full graph, so when we augment the full graph with information from the read sample, we can see that we have a peak here, that it should be a peak at 1, meaning that most of the sequencing errors that are left in the reads by the I5ASM error correction step are actually augmented. So I mean, they will produce a new vertex in the graph. So this is an issue with our approach that I need to fix. So most of the novel vertices in the full settings are due to sequencing errors. And that could be the case even for this peak here in the one out, but we also have a peak at 0, meaning that in the one out, when we augment the graph without that individual with read information, we add some vertices that are not even used by the reads. So meaning that maybe we shouldn't, for sure we shouldn't add those, but we are doing that. So still 94% is quite a high number for our definition of precision, I think. Okay, so these were the results, and I'll try to present. Okay, and yeah, so this is still a work in progress, but results seems promising. So I would say that pangenome graphs actually can be augmented using long reads. So maybe in the future we won't need to assemble the read sample before augmenting the graph. Maybe we can just directly use the read sample to augment the graph. But yeah, this is a work in progress. So there are quite a lot of open questions and things that I'm investigating right now. So this is just a list to improve the precision, just to understand why we're adding those vertices that we shouldn't add. And yeah, we are doing a local augmentation of the graph. So we just add vertices and edges. We are not including the full haplotypes in the graph yet. So it's just enough. We are just updating the topology of the graph, and we are not adding the full haplotypes. But I think that the sort of realignments to the augmented graph can help in phasing somehow the variation that we are adding. And yeah, then I would like to move to more general graphs. So a DAG, as I told you before, the DAG is assuming the second stage of our approach. Then general code improvements. The code is not yet freely available because I'm working on it these days. So it will be freely available on GitHub. And we have some scalability issues. So the RAM usage is quite high due to the sketching scheme that I'm using, so the hash map. And the running times are quite high for the last step because we are doing a pairwise alignment against each unique part of the subgraph, and it is quite time consuming. And yeah, I would like to move the experiment to HPRC graphs, so the big graphs, not from BCF, not built from the BCF, and real samples. And yeah, so thank you. That's from me. I'm glad to answer to any question, if any.
Thank you very much, Luca. Very interesting talk. As usual, we have this delay between the live stream and the chat, so the question might arrive later. In the meantime, I have a question for you, which is sorry if I missed this, but is the augmentation step performed at the read level or at the individual level? Meaning, like at each step, at each read, you try to augment the graph, or you do these alignment steps and this anchoring step for the entire individual and then modify the graph using the sets of reads?
Yeah, it's done from this set of reads, let's say. I'm not considering each read independently. I consider each read independently for computing the specific strings. But then once I have the anchor specific strings, I cluster the specific string all together. So each cluster will contain specific strings anchored to the same portion of the graph coming from different reads. And then I summarize that information.
So when you build this consensus, is it possible that some of the reads do not agree? And
Yes, it's possible. And for that reason, we have all these steps. I mean, one of the problem is this one. So they may not agree even for the anchors. So there might be some problems, and but I'm trying. What I'm doing is I try to extend them even more in order to make them start and end with the same anchors, and it doesn't seem to affect that much the results. And but yeah, and then there are all these heuristics that say that try to clean the cluster somehow in order to understand which portion of the cluster should be considered to then create the consensus and then augment the graph.
okay, and I have another one. In some slides, you were talking about the distance between the anchors, right? And the fact that you wanted that to be quite small. So I was curious about why why is this desirable? I mean, is it because this is the first step, or do you want to avoid structural variation or so on, or you plan to include them in the future and this is just the first step to keep things simple?
Okay. Um, uh, let's say that I don't have any proof of this. So this is just something that I saw in the data,
Mm-hmm.
heuristically derived. But even if you pick the closest one, you can have the structural variations, because even if they are closer, I'm using solid anchors that are unique in the graph somehow. So they are from two vertices of the graph, and my assumption is that if I can find those anchors, they are pretty much the correct anchors. So even if they are the closest ones on the graph, they are the correct one anyway. So if I have a structural variation, so a big deletion with the graph, my assumption is that my solid anchors will be far away on the graph, yes, but still they will be the closest that I can find. So it shouldn't affect that much. So structural variation we should be able to augment the graph with structural variation,
Okay.
even with this definition of best, that is still not the best one.
Okay, okay. That's very good. Thank you. Let me check. I don't think we have other questions. And yes, so thank you very much. The talk was very good and very clear. Thank you again for being here, and
Thank you.
uh, we will resume